Okay, so I see that it is time, so we will start the lecture. So we have the pleasure of having Leon Balents with us today, and normally the moderator was supposed to be Andy Millis, but unfortunately was not able to make it. So been moderating. And Leon will deliver his second lecture, which will be 75 minutes today. And please, as we did before, you can use the chat to write questions. And at the end, you will unmute your mics and speak your questions if possible. Leon.
Merci, Marc. So it's nice to be back. I'm going to speak on a somewhat different topic today, although still in the context of Moire systems. I'd like to start by just recalling some lessons that hopefully we took from my earlier lecture, but also the lectures of Alan MacDonald, which discussed Moire physics of electrons in transition metal dichalcogenides and twisted bilayer graphene. So there are many lessons. I just want to draw the simplest one, which is that in all these cases, these Moire patterns have very, very large unit cells. If they have a unit cell at all, generically two twisted materials relative to one another actually form a quasi-periodic pattern with a a priori infinite unit cell, but practically speaking, there's well approximated by one with a large unit cell, but they're still enormous. They might contain tens of thousands of atoms, and working directly with the atomistic description is rather inconvenient. But we saw in these previous examples that there are continuum descriptions. Which work very well. They're very useful and intuitive. And they have the huge advantage that one doesn't have to keep track of tens of thousands of individual atomic sites. They offer conceptual advantages. That they connect to the standard equations for bands, which are electrons in a periodic potential. And often they connect to transition metal oxide physics, which of course also described by bands, and in particular often tight binding bands. And we saw how these are achieved, for example, in a very simple way in TMD Moire structures. So, in general, in condensed matter physics, continuum limits are not always valid. When a continuum description is something that applies when there is some long length scale in the problem, much longer than an atomic scale. So in this case, a key ingredient is a long Moire length scale. Which is the Moire superlattice has some period A Moire, which is like the microscopic lattice constant divided by, for example, a twist angle theta, which is much bigger than the atomic lattice constant. And when that happens, if you look locally at a range of a limited number of microscopic lattice sites, this intricate Moire pattern locally looks like just a uniform displacement of each of the layers. It may be different relative to one another or relative to some substrate. with those key ingredients, it's possible to construct a continuum theory. And Alan talked in some detail how to do this for TMDs and sort of sketched it a bit more in the case of twisted bilayer graphene. I'll just like to give you a blatant advertisement for a little bit of work of mine, which showed you what I find is kind of an intuitive way to derive this continuum model for twisted graphene structures, which is still rigorous and allows you to study all sorts of Moire patterns. So if you're interested in that, I'd refer you to this article from last year. Okay, so today I'm going to change gears and try to apply these ideas of continuum models to a different class of 2D materials, which are magnetic 2D van der Waals materials. So that the goal here is going to be to explore, and I really mean explore in a theoretical sense. So this is not something which has really been studied much or at all experimentally. Experimentalists are just starting to study the simplest possible phenomena involving van der Waals heterostructures of magnetic materials. But as theorists, we should try to look forward and anticipate what can be studied and will be studied in the near future. I think this is inevitable. So we want to explore effects of Moire patterns on intrinsic magnets. So just a comment on this notion of intrinsic. When Alan talked about 2D TMDs, for example, and twisted bilayer graphene, there was certainly a discussion of magnetism in 2D TMDs, for example, and TBG. It is the magnetism there, however, is induced by the Moire pattern. So that's for example, in a hetero-bilayer of TMDs, Alan showed you how you could achieve something which simulates a triangular lattice Hubbard model, which in the strong interacting limit can be approximated by a system of spins on the triangular lattice with antiferromagnetic interaction. But the ingredients, the TMD you put in there was just a semiconductor. There were no local moments built into that description. Another example is, so we have these 2D Hubbard simulators. Another example is quantum anomalous Hall effect, which, as Alan discussed, involves a spontaneous appearance of an orbital magnetic moment, in addition to Chern bands, et cetera. So this is a type of ferromagnetism, and this is all very interesting and important, but there's another class of 2D materials, which are just different materials from graphene and these semiconducting TMDs, which are intrinsically magnetic 2D materials. That means that they actually have really local moments on the atomic scale, not the Moire scale. They involve transition metal, real transition metal ions that house those moments. So the spins do not emerge. I mean, admittedly, they emerge on the scale of atoms, but they don't emerge on the Moire scale. There are they need to be included as degrees of freedom. This is interesting from the point of view of accessing different types of phenomena and, if you like, simulating other strongly correlated quantum materials, which oftentimes, for example, as in heavy fermion materials, involve a dense system of local moments. Okay. There are actually many examples of van der Waals materials with intrinsic magnetism. Here's one nice review article, which is not complete, but does describe a couple of classes of a very interesting 2D magnetic materials. Is this review article by Maguire? I put the reference here. He discusses mainly two classes of these magnetic materials. So these are basically transition metal dichalcogenides with the structure like this. So some transition metal and two halogens. And there are also transition metal trichalcogenides like these. These are all 2D layered materials in which the transition metal ions carry local moments. In the first class, these materials like titanium dichloride, the local moments reside on a triangular lattice. You can see the blue sites here. Those are the transition metal sites. They're relatively weakly coupled between layers, and you can see many examples in which those magnetic moments form antiferromagnets or ferromagnets of different types. In the second class are systems with a honeycomb lattice structure. Here you can see the transition metal atoms forming a honeycomb lattice like this. This is maybe might be familiar to some of you who study more strongly correlated materials. There's one particular material of this type which has been studied a lot recently in the context of spin liquid physics, which is ruthenium trichloride, that appears on this list here. It's one example of a geometry of edge sharing octahedra. You can see these here, chlorine octahedra sharing edges. So this second structure is, in a way, very similar to the structure of most of the TMD materials that people study, which also have this kind of honeycomb lattice arrangement. And again, there are both ferromagnets and antiferromagnets of different types occurring here. So this that review is really a study of bulk crystals of van der Waals materials. It's not clear which ones of these have actually been exfoliated, but the list of materials that actually have been exfoliated and studied is growing rapidly, but is much smaller. It includes a few of these. And others that are different structure types that aren't on that list. Here's I'm going to take this. So this is an image from oh, that is weird. There's I see that there's some kind of bar appearing here, which it doesn't actually show on my screen. I don't know why, how to get rid of it. No, maybe it doesn't show on yours either. Okay. So this is from a nice review article from, among other people, I learned about it from Alberto Morporgo. This is in Nature Nanotechnology from last year. This gives a bunch of examples of 2D materials that have actually been exfoliated and studied in ultra-thin form. One thing I would note that all these examples, in all these examples, the spins in the 2D layers order. But they may order ferromagnetically, antiferromagnetically with different types of order within the 2D planes. So there are a number of different structures, different sort of magnetic structures that can occur. Let me take these images here. So on the left is a kind of simple antiferromagnetic structure that occurs in manganese, phosphorus, sulfur-3, for example. That's one of the better studied. So here, these are the structure type. The transition metal atoms lie in a honeycomb lattice. Basically, all the ones that have been studied intensively in ultra-thin form have that structure type. And the honeycomb lattice is bipartite. So if you imagine a system with just predominantly nearest neighbor antiferromagnetic interactions along these nearest neighbor bonds here, the spins will just tend to order into a nail antiferromagnet where one sublattice, say the blue one, has spins pointing one direction, and the other sublattice, the orange one, has spins pointing opposite. So this is kind of standard nail antiferromagnet with two sublattice order. If you look at the same structure but different transition metal atoms, replace manganese here by iron or nickel or cobalt. In these cases, actually a different sort of magnetic structure occurs rather than a nail antiferromagnet, what is usually called zigzag. Antiferromagnetic order occurs. Here, again, you have spins oriented in two directions, but the two spins, each spin orientation, rather than alternating, form these sort of zigzaggy stripes on the lattice, and this is quite common. I would remark that this is the same magnetically ordered state that occurs in this example I already mentioned, which is alpha ruthenium trichloride. There's one other type, which has been pretty heavily studied. Which is, which occurs in chromium triiodide and chromium tribromide, which is just a ferromagnet, at least within the layer. Okay. So these are, these are all intrinsic orders. They don't change much. With thickness. Although, for example, the critical temperature may vary somewhat as you change the number of layers. Generally, also, in all these examples, the magnetic coupling between layers is weak. That's not too surprising, as van der Waals crystals generally are relatively weakly coupled electronically and structurally from layer to layer. But direct evidence we can find, for example, from various studies of bulk materials. Just as an example, I would highlight, let's take this example here. These are figures from a neutron scattering study of manganese, phosphorus, sulfur 3 in bulk crystal form. One of the most direct ways to get an idea of the strength of interlayer coupling is to measure the spin wave spectrum. So these are spin waves in the ordered state, measured by inelastic neutron scattering. You can see this is the this region here. This is in plane, the in plane dispersion. And this is a scanning the dispersion relation along the z-axis. And you can see the energy of the magnon changes very, very little as we do that. In fact, they estimate by fitting these dispersion relations, they estimate an interlayer coupling is about 1/4% of the strength of the nearest neighbor in-plane antiferromagnetic exchange in this material. So this ratio is particularly small in MnPs3, but in all these materials, it's a small number, not rarely more than a few percent. What else should you know about these 2D magnets? So of course, there are some details that depend on the ion, as is always the case, and you should have been hearing a lot about this type of physics of transition metal ions in this course, in the school. I mentioned these manganese materials. Here, manganese is in the 2+ oxidation state, so this is a spin 5/2 spin. If we think of octahedral coordination, this corresponds, it actually doesn't depend that much on coordination, but this is 5 electrons out of 10 possible d orbitals. It's a half-filled shell. It forms a largest possible spin according to Hund's rules. It has 0 orbital angular momentum. And because of this, it's very isotropic. So we should expect, to a very good approximation, Heisenberg isotropic spins. In chromium triiodide, for example, we have the chromium 3+ ion. This is a spin 3/2 ion. We think about octahedral coordination again. This corresponds to filling 3 out of 5 of the d orbitals, but they're split that way anyway in a cubic crystal field. So this is kind of another example of not a half-filled shell, but a half-filled subshell. And the effective orbital angular momentum within the T2G subspace is also 0 here. So this leads to another highly isotropic spin, not as isotropic as manganese, but still quite isotropic. I won't go into details of iron, nickel, and cobalt, but these all involve partially filled subshells. Generically, sometimes a competition between different orbital states. They're generally less isotropic. That'll be important at some level. Okay. So what I want to try to get to, though, is get to discussion of Moire physics in these systems. So let's start simple. I want to focus first on the isotropic Heisenberg-like systems. And we'll consider effects of some weak anisotropy. So you may want to be thinking of MnPs3. Anytime we discuss this sort of magnetism of these 2D materials, again, because there's a strong intrinsic magnetism in the material, and generically in these van der Waals materials, the coupling between different layers is weak. our description has to start with an understanding of the correlations between spins that are generated by intrinsic properties of the layers. That means the description will be rather different for 2D materials with different types of magnetic order. For example, if we want to describe these Nael antiferromagnets here versus these stripy zigzag antiferromagnets here, the spin correlations are very different. We'll have a different description basically right from the starting point. Here I want to think about this Nael order. It's the simplest one. So if you want to think about a microscopic sort of lattice model, this would just be some nearest neighbor antiferromagnetic interaction between spins. But I want to emphasize that actually assuming that is not necessary. It's simply a way to understand the Nael order that occurs in the system. Okay, so this will lead to, such a model would lead to a Nael state. You should have in mind spins on this honeycomb lattice. Within this Hamiltonian, at low temperatures, what will happen is the spins will have opposite alignment on the two sublattices, but the direction in which the spins point in spin space is undetermined. Okay. So this is a feature of these very low anisotropy systems. This is described theoretically by an order parameter, which is a Nael vector, n. When it's isotropic, the direction of n is arbitrary. So now we want to ask the question, okay, what is the effect of Moire pattern on this? So suppose we have two layers coupled by some interlayer interactions J prime. So if we tried to approach this atomistically, we'd have some structure like I've drawn here. Although typically the Moire patterns that are studied involve much smaller angles than this. This is a pretty large angle. And consequently, the unit cells would be a lot bigger. The Moire cell would be a lot bigger. If we tried to understand this thing atomistically, it would look very complicated. Why is it complicated? Well, if you ask, which spins are nearby and what their environment looks like, it varies enormously from place to place. So, one would atomistically have to search through this structure and decide, okay, what spin is close to one other spin in a nearby layer? For example, over here, it's pretty clear that we can identify one spin right on top of one another. In some region like this, it becomes quite a bit more complicated. Some spins are nearby others, some are not. There's some situations here where the spin at the center of this region is kind of equidistant from others. How do we think about the interactions there? An attempt to study this would involve microscopically, there would be a huge unit cell with very diverse interactions. But inspired from the success of continuum models of Moire bands for electrons, we can try to use try to develop a continuum approach for magnetic interactions, for magnetism. Okay, where we can forget about these atomistic details as much as possible and have a minimal description. So what we use really is this fact, two facts. One is that layers are weakly coupled relative to one another. As I said, this is a feature of all these van der Waals materials. And also that the Moire wavelength is much bigger than the lattice spacing, which means that locally the system looks relatively uniform. So under these two conditions, we know that the local order of each layer should be described by the order parameter for the magnetism that would occur if that layer were isolated. Here, by a slowly varying, it's slowly varying because of the long Moire scale, Néel vector. So here, this can be different in different layers. We put a layer index and it will depend on the position. Then what we can do is we can write down the energy density for two coupled layers. So this is like writing down the Hamiltonian for the continuum model for two coupled graphene layers, for example. That energy density will involve the energetics of a single layer, and the basic physics of that energetics is simply that in the absence of any perturbation, the Néel vector would like to be a constant. Any attempt to rotate the spins away from the preferred staggered pattern will cost an energy, which is related to the exchange interaction times the angle of rotation. So that's described by a very universal term, which is something called a spin stiffness. And that rho will be proportional to the nearest neighbor J, for example, the microscopic exchange scale of an isolated layer. For two coupled layers, we'd have spin stiffness for both layers. In these very isotropic systems, there'll be a weak anisotropy term, but it's still there. For example, in MnPS3, there's a weak Ising-like anisotropy that makes the moments prefer to order out of plane in a staggered fashion. And this is some small energy, I'll call it D. D will be much less than J, and there's a factor of the microscopic lattice spacing, just on dimensional grounds. So this is kind of the intra-layer energetics, and then there'll be some coupling between the layers. So generally that involves some coupling scale J, and locally for something with approximately Heisenberg symmetry, it'll just involve the product of the two spins in nearby layers. So in other words, a product of the two order parameters. But importantly, the way they couple depends on the local displacement of one layer relative to another. So in general, we can imagine slowly varying displacement fields describing distortions, rotations, translations of each layer separately. What we know from symmetry is if we translate both layers together by the same amount, all we've done is change our origin in space And so the coupling between two layers can't change. So it can only be a function of the interlayer displacement, relative displacements between the two layers. But it will definitely be a function of that. A simple way to see it is, let's imagine we just have a simple antiferromagnetic superexchange. Between nearby ions. In that case, if we have AA stacking, so we have two layers right on top of one another. Okay, I'll draw one layer in black and one layer in blue. You can see that the spins, a spin on the black layer wants to be anti-parallel to the nearby spin, the one right above it, on the blue layer. And this clearly prefers N1 equal to minus N2. On the other hand, if we had stacking of the form, for example, AB stacking, so that looks something like this. Then if we have antiferromagnetic spins on the black lattice, the blue spin here wants to be anti-parallel. Okay. But actually, if you look and you compare the configuration of the two A sublattice spins, okay, so this is an A sublattice site on the black sublattice, and here's an A sublattice site on the blue sublattice. They're actually parallel. So in this case, we actually want N1 equal to plus N2. So in general, this J of U varies and changes sign even on atomic scales. We know it should be periodic. Because if we translate the whole system by one lattice spacing, we haven't changed anything. So it means we can expand J of U in a Fourier series. So a good approximation should be gotten by just keeping the first few components. This is J prime. There could be a constant term, and there can be terms at the lowest reciprocal lattice vectors. BA are the reciprocal lattice vectors of the graphene honeycomb lattice. Has to take this form due to reflection symmetry. What are these values? Well, okay, a very simple kind of derivation of this is to consider the spin density in real space. So really, these spins, due to these manganese ions, they live in some atomic orbitals that has a continuous spin density, which of course is localized around the locations of the atoms. But nevertheless, there's a spin density, which is a function of position. If we were to write it, it will be, the orientation will be determined by the local Néel vector. And it's periodic, so it can be expanded in a Fourier series. And it's straightforward to show that Fourier series actually involves a sign of the reciprocal lattice vectors of the honeycomb lattice BA. If we have a little bit of displacement, we should shift this by the displacement field because that shows that's where the center of the atoms move. So the fact that it's sine and not cosine is something you can easily see by just drawing here. For this convention, I've taken the origin at the center of a hexagon. And remember that the antiferromagnetic order looks like this. we have opposite spins on the two sublattices. You can see that if I were to do a C2 rotation around the z-axis or a spatial inversion, I exchange spins of the two sublattices. And so the spin density is actually odd under that. That's why it's sines rather than cosines. So now if you just imagine some integral of the spin density between the spin density of layer 1 and spin density of layer 2, some local interaction, so the spins just interact vertically when they're nearby, you can plug this in for each of these two spin densities. You get a product of sines. You can expand the product of sines as a cosine of the sum and difference of the arguments. There'll be a highly oscillatory part, which averages to 0, and the non-oscillatory part is approximately like this. It involves n1 dot n2 times the sum over A of cosine BA dot u1 minus u2. So if you compare that to the previous form I just wrote by the Fourier expansion here, you can see this gives the same above form, but with j prime 0 equal to 0. So we expect that this is a good approximation. Basically, there's 0 average coupling between the layers because they're two antiferromagnets, which have no net magnetization. In general, that won't be exactly true. And for example, we can get J0 prime bigger than 0, but still much less than J1 prime by lattice relaxation. But for the sake of simplicity, we'll take that to be the case. Okay, so we'll just assume J prime of U is this J1 prime sum on A cosine BA dot U. So now we can take that and study the situation of a twist. In a twist, the relative displacement of the two layers now depends on position linearly. So the twist between the two layers is described by a displacement which is orthogonal to the distance from the axis of rotation. And the coefficient is just the angle theta. If you plug this in, you get that J prime of U is J prime sum on A cosine BA dot theta Z hat cross X. And we can use the cyclicity of the triple product to write this as cosine of theta Z hat cross BA dotted into X. So this defines a wave vector QA, which is theta Z hat cross BA. It's a small wave vector proportional to theta. These are just the reciprocal lattice vectors of the Moire lattice. And they appear very much the same way those appear in the continuum model for twisted bilayer graphene, for example. So putting this together, we get an energy density, which is quite simple. For each layer, we have a spin stiffness and a small anisotropy. And then we have a spatially dependent coupling of the two Néel order parameters where this function phi of x is just the sum of these three harmonics, three elementary reciprocal lattice vectors of a hexagonal unit cell. So this thing, this is analogous to the continuum model for the bands in a Moire structure. Okay. One thing I would point out, there is one important difference, which is, as I've written it, H here is classical. It just is a function of the two order parameters in each layer, which are classical variables. There's nothing that doesn't commute with itself. So it really describes only the energy density. In more theoretical terms, not the Lagrangian, for example, or doesn't include a conjugate variable, a conjugate momentum to those Néel vectors. So is that okay? You might worry, well, okay, you know, real spins are not classical. These manganese spins had S equals 5 halves, but the chromium spins have S equals 3 halves. There are examples where they're even smaller. Ruthenium trichloride has an effective spin 1/2, for example. They certainly are still quantum. They have quantized energy levels in a magnetic field, for example. So are we losing a lot of physics with that? The saving grace here is that the number of spins in a Moire unit cell is huge. And because these materials exhibit magnetic order, they act collectively. Because of strong correlations within the 2D layers, and hence the order parameter are really semi-classical. They're not fully classical. They do have some dynamics, and we can come back to include that later, but the classical energy density is a good starting point, at least to identify the types of magnetic structures that will result. Okay. So if we look back at our Hamiltonian here, this is really the Hamiltonian on the first line. Okay. This Hamiltonian density, you can see that there are actually two dimensionless constants defined here. Why is that? Well, you know, rho itself, d and j prime, they're all dimensionful quantities. The physical properties at zero temperature can only depend on ratios of them. And in particular, if we can make dimensionless quantities using the intrinsic length scale of the Moire pattern, that is the Moire wave vector q, which is you know, proportional to the angle. So if we start to identify dimensionless parameters, those dimensionless parameters are j prime divided by rho times q Moire squared. So that's kind of easy to see because the gradient is an inverse length scale. It scales like a wave vector, so this term scales like rho q squared. The denominator is the energy cost of twisting the Néel vector by an order 1 angle over a Moire unit cell. And the numerator is the amount of energy we could get from interlayer interactions. So this is one dimensionless parameter alpha. And there's a second one, which is measuring the strength of the anisotropy in the same terms. So d over this. And the thing to remember is the Moire wave vector is proportional to theta. Intrinsically, both J prime and D are small energy scales. They're intrinsically much smaller than the exchange scale rho. If the Moire wave vector were of order 1, that is of order the lattice scale, these would all be tiny parameters. But as we reduce the angle, the denominators get small, and so these can become of order 1 or even large as we make theta small. So consequently, there's a sort of two-dimensional ground state phase diagram, which is really answers the question of how do we minimize the energy, the integral of this energy density for different values of rho, d, and j prime. Okay, and here's what it looks like. We'll sort of dissect this one bit at a time. I've drawn this in a way which allows you to make the axes vary between 0 and 1. So the horizontal axis is alpha. So this is, remember, this is basically the strength of interlayer exchange interactions. So when alpha is small, the layers are weakly coupled magnetically. When alpha is large, alpha over 1 plus alpha goes to 1. So this axis equals 1 means infinitely strong interlayer interactions. The vertical axis is the strength of anisotropy. So when it's large, the spins really want to align along the plus or minus z-axis out of the plane. Okay. So let's consider various limits we can understand this diagram. So first, let's suppose beta, which is equal to d, is equal to 0. Okay, so we have no anisotropy. This is the Heisenberg limit, and we consider large alpha. So this means j prime much bigger than rho qm squared. So in this case, we can just approximate our Hamiltonian. We can neglect the gradient terms, and we can approximate our Hamiltonian. Oops. Sorry. By just the interlayer interaction. So this means that stiffness can't compensate for the interlayer interaction, and the spins are just going to minimize this term. Well, clearly this is minimized by taking n1 parallel or anti-parallel to n2. So in particular, we have n2 should be equal to the sine of phi times n1. So if phi is positive, we want n2 parallel to n1. If phi is negative, we want n2 anti-parallel to n1. Okay. Well, phi is this function, sum of the three harmonics. You can see it doesn't contain a q equals 0, so it has 0 net average. So clearly it contains both positive and negative regions. If you actually plot the sine of phi over a Moire unit cell, you'll see that there's a region near the origin where it's positive and a region outside where it's negative. Physically, the region near the origin corresponds to the AA region. And these the corners correspond to the AB and BA regions. Okay. There may be an overall sign here I'm getting wrong. Yeah. So basically what will happen in this kind of strong coupling limit, so this is on our diagram here, this corresponds to this region here. We've taken no anisotropy and very large interlayer coupling. In the center of the region over here, we want n1 equal to n2, but everywhere here we want n1 equal to minus n2. So clearly, to get from one to the other, the spins have to rotate. In the strong coupling limit, they rotate in a very narrow region around this boundary where where this function phi changes sign. Okay. So we can ask the question: how do the spins actually interpolate? How do they actually rotate between these two regions? The way to do it theoretically is to solve the variational problem. The variation of the Hamiltonian, which is the integral of h of x I'll write this as, I'll put a subscript on here to indicate this is classical. So this is a calculus of variations question. I'm going to find the minimum energy configuration of these Néel vectors. I should have mentioned, I don't think I mentioned it at any point, we have a constraint that the length of these Néel vectors is 1. Okay, so the spins have to point in some direction. So this is a calculus of variations problem. It results in 2 partial differential equations for the Néel vectors in the 2 layers. One can show that the solutions are always coplanar. So that kind of makes sense for this model. We know that, for example, in the interior region, the spins, let's say, want to be, the Néel vectors want to be parallel, and the other region, they want to be anti-parallel. You know, at least one of them has to rotate, but there's no reason for them to go out of one plane of rotation. They want to minimize the spin gradients as much as possible because there's a penalty due to the spin stiffness rho for any gradients. So this should be pretty plausible. It means you can write, so we can solve the constraint and reduce the degrees of freedom to 1 angle per layer. We write NL as cosine phi L. We choose this plane to be, for example, the ZX plane. The plane should always contain the Z-axis because the spins preferentially align along Z, at least if we have any anisotropy. And so we'll get 2 coupled nonlinear equations for these 2 angles, phi 1 and phi 2. It's convenient to write this in terms of symmetric and antisymmetric combinations. And one can show that these equations are of this form. So this is all in dimensionless coordinates. Basically, we've scaled things so that the length of the Moire wave vectors is 1. So you can see these are kind of nonlinear Poisson type equations. If you stare at this for a while, you can find some trivial solutions. For example, one thing one notices is that if we take both phi s and phi a equal to 0 or equal to pi, this is always a solution. This is actually the trivial solution. It's not the energetic ground state. It's never the energetic ground state, basically. But there's generally, there's a subset of this, a simple thing, which is always a solution. If you take phi s equal to pi, this is always a solution. So that satisfies the first equation here. You can see phi s equal to pi, the sign vanishes and it's constant, so the Laplacian vanishes. If you put phi s equal to pi here, this just becomes -1. And then we can still have a non-trivial function for phi a. This is a vector. So this turns out to be the correct form for the ground state in a large region of the phase diagram. We call this the twisted S phase because it has some simple structure for the S symmetric part of the phase. This statement that phi s equals pi here, actually what it means physically is this, although one has a magnetic texture in which both the Néel vectors in both layers rotate, there's a hidden symmetry of that pattern. That is, if we interchange the 2 layers, so reflect in the plane z to minus z, and do a C2 rotation around the y-axis. That is a pi rotation in spin space around the y-axis, which takes nz to minus nz. This pattern is preserved. So that, if we go back here, that corresponds this whole region here, and in particular the entire region of the horizontal axis here where there's no anisotropy is described by this twisted S phase. Okay. So what does this thing look like physically? So to really show this requires some bit of applied math analysis of this equation, and one can do a certain perturbation expansion of it in the small alpha limit and understand it also for alpha much bigger than 1. What it looks like if we were to draw the configurations of these order parameters in the Moire unit cell, in the center, we have, so here the upper vector is the vector in the upper layer and the lower vector is the vector in the lower layer. Here, these ends would be parallel. Out here, they want to be anti-parallel. And in fact, what happens is in this case, the spins deep in the interior region are almost perpendicular to the spins in the exterior region. And so to rotate from one to the other, what happens is the spin on the top rotates counterclockwise as we move to the right, and the spin on the bottom rotates clockwise. So in between, we have some pattern like this. Okay. So that's what this twisted S phase looks like. So spins in opposite layers rotate oppositely, but only by 90 degrees. So one thing you can notice is this is obviously unfavorable from the point of view of Ising anisotropy. And so this becomes disfavored as we increase D. And in fact, what happens is with increasing D, there's another possible solution, which we call twisted A, which breaks this symmetry involving layer interchange. Basically, in this case, there's a non-trivial solution for both phi A and phi S, and phi S is not equal to pi. Here you can imagine that, let's say in the interior, the spins are both along the plus Z axis, and the exterior one's along plus Z and one's minus Z. And now you can see, that the situation between the two layers is very asymmetric. The bottom spin has to rotate by 180 degrees, while the top spin doesn't really have to rotate at all. So that's the reason why this interlayer exchange symmetry is sort of broken here. The top spin will rotate a little bit, but it'll rotate back. So this is the more complicated spin texture. And finally, there's the third phase is a collinear phase that occurs when D is very large. So if we go back to our phase diagram, I'll copy it over again. Now we can understand all these phases, okay? Here's the twisted S phase. This really occurs for most of the region of small anisotropy. There's a collinear state, and this twisted A phase is something that occurs when the layers become more strongly coupled. You can ask about the transitions between these phases, and I don't want to say too much about it, except that, in fact, what happens here, this is kind of very typical sort of phase diagram when you have two types of orders with a, I guess it's called a tricritical point. where the two phase boundaries coalesce at some point, like here. The two boundaries up to these points are described by continuous transitions, but there's an endpoint of this line, which is a first order line, where the system goes directly between the twisted A and the collinear. So one thing to note is I've chosen for convenience to draw these axes in terms of these funny variables, alpha over 1 plus alpha. If we think of a physical system, we can imagine varying the twist angle theta. That keeps, that'll keep rho over J prime and rho over D fixed. That actually corresponds to these dashed, for example, trajectories on this plot. They're not straight lines on this plot. No one can show, for example, on the lower trajectory, the system for, this would correspond to large twist angles here. And over here, as we get up here, this is small twist angles. As we decrease the twist angle, we'd go through this twisted S and then to twisted A phase here. In this case, we'd start in the collinear phase, and it's not quite clear from the figure what happens, but actually one can show that for small enough angles, theta goes to 0, it always as it enters the twisted A phase. So in principle, no matter where you start, basically, by reducing angle, you should be able to induce phase transitions between these different states. And really, of course, the two interesting states here are the colorful ones at the bottom, the twisted phases. These have magnetic textures whose scale is determined by the Moire pattern, so it varies smoothly with the angle theta. The other thing you could vary in an experiment easily would be an applied magnetic field. I won't really have time to explain this, but it turns out that for an antiferromagnet like this, it actually, applying a magnetic field along the z-axis is effectively like reducing the anisotropy D. So we can move up and down vertically on the diagram. Not up, actually, only down by applying a B along the Z direction. Okay. So it means this thing can be tuned in situ. Okay, I think I have about 10 minutes before we go to the discussion time. I like to kind of move on. I will run out of time. Let me talk about a few more aspects. One of the interesting things to think about with a view to experiments is what the excitations are for these states. These are magnetically ordered states, so we expect them to have magnon modes or spin waves. But because they involve very large unit cells, the Moire unit cell, there will be a lot of magnon modes. The usual counting of number of modes is that any given spin has two magnon modes associated with it, because that one spin can rotate in two possible directions relative to its local ordering direction. So the total number of modes should be 2 modes per spin per unit cell. So for these Moire patterns where we might have, small angles might have 10,000 spins per unit cell, we'll have 20,000 modes. So that's a very big spin wave problem. Again, would be very unwieldy to study by usual, for example, Holstein-Primakov methods. But actually, again, a continuum description applies to those modes. To really calculate them, one can simply use this semi-classical description. It'd go from a Hamiltonian to a Lagrangian. Lagrangian involves just a kinetic term for this Néel vector. And as usual, Lagrangian is kinetic minus potential energy. So we should subtract, this is the Lagrangian density, subtract the classical Hamiltonian density here. Okay. So this describes the dynamics of an antiferromagnet. The important parameter here, new parameter, is the bare spin wave velocity. This is the bulk spin wave velocity. So for an antiferromagnet, the spin waves have linear dispersion. They're described by some sound velocity. That's the sound velocity of the isolated 2D material for in-plane spin waves. And one can just expand this. Again, one has to treat this as a unit vector, so we can expand it around the classical solution by introducing some local coordinates. These are unit vectors, UL and VL, which are form an orthonormal frame relative to the local classical vector. And remember, this depends on the position because there's some structures. So we have to solve for the classical ground state, solve these partial differential equations that obtains this, and then we construct an orthonormal basis. Plug this in, expand it to quadratic order, u squared, v squared, uv. That gives the Lagrangian and the corresponding Euler-Lagrange equations. Describe the spin waves, and there are some wave equations. Okay. It's a continuum model, and because it's a continuum model, there'll be an infinite number of bands in those wave equations. I can show you what they look like. So this is just one example. This is an example for the case of zero anisotropy. So in this twisted S phase, and one can see on this plot that there are actually, complicated, interesting band structure for these magnon modes. And it has the property that there are several acoustic modes going down to zero energy. Those are acoustic magnons. They're the Goldstone modes. So with no anisotropy, actually, it's interesting. There are 3 acoustic modes. That's because this is a non-collinear spin order. Generally has 3 rather than 2 acoustic modes, like a more conventional Néel antiferromagnet. When you include anisotropy, generally 2 of these will develop a gap, but there'll still be 1 gapless mode. Again, different from the isolated layer. And there are lots of interesting features. I don't have time to go into it. For example, as we go to small twist angles, many of these modes become very flat. So we can have very flat magnon bands, very much like we have very flat electron bands. Maybe interesting. In the interest of time, it's difficult for me to go into too much detail, but one can study all types of other different magnetic orders. What I've talked about is just the situation with two sublattice antiferromagnets, but the general procedure involving coupling order parameters can be, and the resulting continuum model can be applied to any type of 2-dimensional order, including what might seem trivial, which is a 2D ferromagnet. Oops. The 2D ferromagnet seems like an unlikely situation to find any interesting physics, because in a ferromagnet, the magnetic order is just uniform. Who cares if you twist one layer relative to another or displace one layer relative to one another? Why should the ferromagnetic coupling really matter? But in fact, we believe, at least in some of these van der Waals ferromagnets, it does matter. And actually, it should matter in the most studied case, which is chromium triiodide. And the way we know it is that actually there are a number of experiments that point to a strong dependence of the interlayer coupling on relative layer displacement. In fact, it's known, for example, that stacks of very small numbers, 1 or 2, 3 layers of chromium triiodide orient differently relative to one another than they do in the bulk. And this is believed to be because of the differences in alignment between layers. In fact, there are some nice DFT calculations. They've been done actually by several groups, but I'll refer to a paper by Sivadas et al. This is in the group of Craig Fenney from 2018. These guys calculate J prime of U from DFT and show that it has sign changes. So this is exactly the object we need as input to construction of our continuum model. And so my student Khosra did that exactly and took their calculations and plugged it into the continuum structure to get predictions for the magnetic structure. And that's, I'll just show you a plot of that. What you can see here, maybe I could make it bigger. Okay, I won't try. Is that this results in interesting modulation of the total magnetization. There are some regions where the magnetization of the two layers likes to be anti-parallel, so there's no net magnetization, and other regions where it likes to be parallel. And so actually the uniform magnetization is modulated on the Moire scale. And whether this happens depends, again, on the competition between interlayer coupling and anisotropy. And so we believe this occurs for angles below about 6 degrees. We expect a modulation, this type of modulated ferromagnetism. I'm going to skip ahead to the conclusion since I'm basically out of time. I had a little bit of more material about these zigzag phases, but we'll skip it. And I'll just summarize. So I've explained how to construct appropriate continuum descriptions for spins in intrinsic Moire structures of intrinsic magnets, and together with earlier discussion from earlier in the week about electrons, we have appropriate continuum descriptions for both electrons and intrinsic spins in Moire systems. In magnets, this leads to controllable magnetic textures. I think this is a very rich and largely open field. There's a lot of things to do in the future. In the future, it'll be interesting to think about other textures. What really jumps to mind in this regard are skyrmions, which are observed intrinsically in a number of non-centrosymmetric ferromagnets, typically as a result of DM interactions. What's the interplay of these DM induced skyrmions with this type of Moire physics? That should be very interesting. Since we have continuum descriptions for spins and continuum descriptions for electrons, it's pretty obvious that these should be combined. And that should further enrich the electronic physics of these, if you like, Hubbard model simulators, for example. And kind of most importantly, we should really see more experiments on Moire magnetic systems, which I'm sure we'll see in the next few years. So let me just leave you with a reference for the work I talked about today, and I'm happy to take any questions at this point.
Okay, thank you so much, Leon. It was very nice, very nice. I really enjoyed it. And now the The session is open for questions. So as we have done, if you have questions, please use the chat feature and do so. And in fact, in the meantime, so I'll take advantage of my host status to shoot first. Actually, you sort of mentioned for the future directions. I was going to ask a let's say a less complicated maybe question that what about skyrmions, but nevertheless for these let's say if we take even single layers of these triangular or hexagonal lattices, it is quite common that there would be more than nearest neighbor interactions, and they could be, let's say, genuinely, intrinsically spiral states or more complicated things. So my question is, how robust is, I would say, the description you gave of the bilayers to these kinds of states?
Yeah. Yeah. Okay. So that's a great question. Thanks, Mark. So let me kind of pull back to the beginning where I was overviewing different materials. Here's let's see, there's a little bit of lag. The point I wanted to make is that generally in these van der Waals heterostructures, the interactions between layers are much weaker than those within the layers. Within the layers, they may be complicated, as you say. There's no reason these things need to be nearest neighbor systems. They could be further neighbor, et cetera. You know, that's clearly the case in these, which I didn't have a chance to talk about very much. These which have zigzag order. This is very unfavorable from the point of view of nearest neighbor antiferromagnetic interactions. So generally, these systems have more complicated further neighbor interactions, probably also anisotropic interactions. That's definitely the case in ruthenium trichloride, probably in the cobalt and iron systems as well. And you know, there's no reason to think that only nearest neighbor interactions are present in the manganese ones, even though they have a simple order. However, what is true is that whatever order is present in the isolated 2D layer can only be weakly modified by these weak interlayer interactions. And so what's really important is not the details of the microscopic interactions on the lattice scale. It's a low energy description. How does the system respond to small displacements, deformations of the magnetic state? And that's a much more universal description. So the nearest neighbor antiferromagnetic description of the 2D Néel state is not robust. You know, they may require second, third neighbor corrections, other anisotropies, et cetera. But the low energy description, you know, here, in terms of a spin stiffness and an anisotropy constant D, this is very robust. So this is like the universality, for example, of the Landau-Lifshitz equations for ferromagnets. Even though ferromagnets, you know, typically involve, they're not even really described by local moments. Usually, it's more a complicated electronic interaction, which rather non-local. Nevertheless, if we only study long wavelength deformations, which is the case here, all these complicated interactions get kind of subsumed into you know, a single small number of constants like the spin stiffness and the anisotropy D. So that's the power of the continuum approach. Is these unknown things are actually not that important. Of course, they're very important if they just change the nature of the ground state entirely. But that we know from other studies. So you know, if we wanted to address iron, phosphorus, sulfur 3, for example, we'd need a completely different description that I didn't have time to talk about.
Okay. I mean, I had a slight follow-up, and then I noticed Igor has a question. But in terms, so experiments versus theory. So these J prime, they're tiny. I mean, they're small numbers. So temperature would affect that drastically. So from an experimental standpoint, do you think, or how would you say easy it is or difficult it is to, let's say, to attain these phases that you described, like the twisted?
Yeah, okay, another good question. So the smallness of J prime, tells you that the energy of interaction of, for example, a single pair of spins in neighboring layers is small. But the power of collective behavior really amplifies that effect. So, this is it really, the appropriate energy scale is the number of correlated spins within a layer, their net interaction with the number of correlated spins in another layer. Okay, so that number is enormous. So even though the intrinsic energy scale is small, actually, they add up to something which is very important experimentally. So yeah, sorry, I didn't have room in this to show you much experiments, but for example, in chromium triiodide, you can see this this interaction scale and probe it directly by introducing applied magnetic fields. So if you have a system of two ferromagnetic layers which like to be antiferromagnetically aligned, no twisting here, just uniform. They're coupled by this weak energy scale, but then you apply a magnetic field that wants them to align parallel to one another. You can cause one of the layers to flip. And that's easily detectable electronically. So that's a way in for example, in electronic measurement, you observe this J prime scale.
Okay.
And the smallness is actually good because it means you can actually compete with that small scale with sort of laboratory magnetic fields, for example.
Great, thank you. So Igor, please unmute your mic. Can you do that?
Yes. So I wanted to ask about the coupling between layers in the model that you have introduced. What is the justification to have a scalar product? Is it on the rotational invariance or something else?
Right, yeah. So the rationale is that, for example, for these manganese systems, we have very isotropic spins. So they're this half-filled shell. It has no orbital angular momentum. So consequently, there's very weak effects of what already is weak spin-orbit coupling in a 3D electron system. So it is very typical for manganese magnets to have tiny anisotropies. So that's the justification, basically. So smallness of spin-orbit coupling means that we have almost Heisenberg SU2 spin rotation symmetry. That violation of spin rotation symmetry is important. That's why we include this D interaction. If I go back to this energy density here, okay. One should remember that there are several sort of small factors. So within a layer, it's important to include this anisotropy, but D is very small, as I mentioned, okay, and that's there. Now, when we couple layers, the coupling between layers is also small. If we were to include anisotropic coupling between the layers, that would be sort of two smallnesses combined. So that's why we do not include the anisotropy in the interlayer coupling. We expect the dominant coupling for any type of interaction will be isotropic, and then there'll be small corrections to it.
Can it be vector product?
It has to be a scalar because it's an energy.
Well, squared.
Okay. In principle, we could have something like that. Yeah, I mean, we could. That's equivalent to writing n1.n2 quantity squared. Okay. So generally, these are kind of small effects in magnets. So this is something related to, for example, biquadratic exchange. So interactions that are higher order in spin operators generally are weaker. To get such an effect, for example, if you think about deriving the underlying spin Hamiltonian from a Hubbard model, the ordinary bilinear exchange, SI.Sj, is second order in T over U. It's a T squared over U effect, whereas these higher order exchanges are T to the 4th over U cubed. Generally, they're pretty weak. There are examples, but they're very rare where they can be important. Usually that's in low spin systems. It can be enhanced by spin lattice coupling. It's quite exotic. I'll just say that that's not something you would first turn to. But,
okay. Are you satisfied with the Leon's answer?
Yes, thank you.
Okay, great. Any additional questions? Okay, there is one. Yes.
Oh, hi. Do you hear me?
yes.
You of course focused here really on the long wavelength behavior in the planes, but of course these honeycomb magnets, as you know, have magnons out in the zone, have Dirac points.
Of course, yeah.
And you know, when you make bilayers, of course, then stuff can happen to these Dirac points. Have you calculated that? Could you maybe tell us about what happens when you have twisted bilayers to the Dirac points for the magnons?
No, I haven't. So I think there has been a little bit of work thinking about that. That's an interesting question. We were focusing really on the effects on the ground state, which are long wavelength.
Yeah, yeah.
But that's something which could be described, but would be described by a different continuum description, because we're really
that's right. So
near zero here. Yeah, that's an interesting question. If there were some, if there were some data on that, it would be interesting to think about.
Well, there's certainly data on the trihalides. I mean, there's experimental data that goes back 50 years.
I don't know of any twisted data, certainly on the bulk.
On the bulk samples, and those
I know some recent work on that as well, I think.
Yeah, and of course they're the same, and then people like Peng-Cheng Dai and so on have been working on looking at revisiting those materials, and there's some interesting things that go in. And of course that's where also topological effects like edge modes and so on can come from.
Yeah, that's very attractive from the point of view of neutron scattering. These are good energy scales and things to look at.
Well, actually, the edge modes are not attractive for neutrons.
Oh no, not edge modes.
But in essence, it's just there's an interesting question. I was just wondering if you thought through what the continuum model would look like near the Dirac points, and then how it would be modified.
No, I haven't, but I can imagine you can do it in similar ways.
Great.
Okay. Any additional question? Last chance. Okay, well, if not, thank you so much, Leon, and especially on a Saturday and early in the morning. With that, I will thank all the participants for following today, and we will reconvene on Monday at 10 a.m. Paris time. So thank you once again.
Thanks, Mark.